Chem problem here. So this is actually more realistic to how it's going to look in the idea that we have half reactions already given to us. These are reduction potentials. They're always given to you as a reduction potential because the electrons are on the left. Reduction involves gain, oil rig. So electrons need to be on the left. So this one's unique, and that's why I wanted to use this one. You'll notice before I even look at everything else, is that the cell itself has 2 PT electrodes. Those are platinum electrodes. Those are not reactive. Right? Those are inert. Those facilitate the transfer of electrons. It's actually all the other ions. So sometimes you'll see it like this. The wire comes down, and it'll be like this, and it'll say something like hydrogen gas, but then they'll have a little wire that says PT. Well, they're bubbling, and then usually there'll be bubbles all on here. They're bubbling hydrogen gas. Well, hydrogen gas can't carry a current. Now, you got to have metal to do that. So they facilitate that transfer with platinum. So platinum's not part. You can look at it. Look at the equation. There's no PT in there. Okay, so that actually makes it in a lot of ways a little more difficult, but you got to realize that that's kind of what's happening. So it says the galvanic cell and the balance equation for the spontaneous cell reaction are shown above. The 2 reduction half reactions for the overall reaction that occurs in the cell are shown in the table below. First off, the minute they say this, that means I have a positive E for my voltage. Okay? If they say spontaneous, that is what it means. So automatically this is going to flow in the direction that makes this spontaneous. So right away it says A, clearly label the cathode. Okay, well we can figure this out. If you look at this, unfortunately when you look here, it goes, well, okay, I got Fe2 plus and Fe3 plus. They're both here. And I have MnO4 minus and Mn2 plus. They're both here. I don't know which way this is going because they're both on each side. That's where this comes into play. Even though you haven't been asked yet, it actually probably is an easier question if they ask what the voltage is first, B, but they're actually asking secondly. So which one do I have to flip? The top one, right? So I'm going to have to flip that one. So I just want to flip that for a second. I'm going to write it out. If I can see this, it's a little hard for me. Is it Fe2 plus? Is that right? Am I writing this right? Okay. For some reason, maybe I'm just too close. So now, that actually matches up, by the way, which makes sense, right? There's the Fe3 plus, right? The Fe2 plus is on the left. You're like, well, how does that help me? It helps me a lot. Because what I am doing is I am actually seeing where the electrons are now. So first off, cathode. What does that mean? What's happening at a cathode? Oxidation or reduction?
Reduction.
Reduction, a red cap, right? Red cap. So, where is the reduction happening? Left or right? And if you're like, I don't know what the right, you're literally labeling one of the 2 cells. The right one. Because this is oxidation now, right? And if you're like, I don't even know. Guys, I think they actually, yeah. If you were totally lost, you get it at a point, they actually told you these are reductions. So if you were like, I can't remember which side's on which. So by flipping it, it's automatically oxidation, right? Well, this is gaining. So the electrons have to be going towards that cell. Well, reduction happens at the cathode. So this is still reduction. So this is my cathode. Right, this must be my anode. So you could have labeled it any way. They just said the electrode in the beaker on the right should be labeled. There's one point. Okay, but that's how I figured it out. So it didn't tell me anything else. Calculate the value of the standard potential. Well, I almost already did it. Assume you got to show your work. So what I would just do is this. And you can subtract it. I get it. I flipped it, right? The key component of that. You got to flip it. You can't just add them up. You got to make sure you flip the proper one and make the largest. How do I know which one to flip? The largest positive value. There are situations where you can flip either one and still have a positive value. Then flip the largest one. There are weird scenarios. But you get it, and it should be 0.72. That's just a point. You should be able to do that. We're just seeing if you know. Again, when you're in this moment only, it's easier. Like, hey, I remember that. But then when you got to bounce back and forth, it gets trickier. So that's why we just have to make sure that we take some breaths and we understand what we need to be doing. By the way, let me ask you this. I don't think it asks. If I asked a common question is draw the electron flow, is it going clockwise or counterclockwise right now? Clockwise? Because it always goes from the anode to the cathode. And you're like, but I feel like it always goes from left to right, except the time that will be asked. You know, that'll be when it is. So technically right now it is going this way. I just want to touch on this. If you ever are confused though, it's because this is gaining and this is losing. So these electrons are leaving this. That's what that means. And these electrons are gaining. That's why it's coming down this way to these. So if you're ever stuck, like, I don't understand, by the equation itself, it tells you the secret. So just know that. Okay, letter C. Kind of all over the place here, but I'm going to write it up there. How many moles of electrons are transferred when 1 mole of MnO4 is consumed in the overall reaction? Okay. If you look right here, don't let that throw you off. You have 1 mole in that equation right now. So this equation represents the balance equation from these two. That's what it's representing. So what do I need? You got to remember when we add reduction, or when we add half reactions, let's just call it that, what's the one thing that has to be equal? My electrons, right? So you can look in here all you want, you're never going to find them, right? You got to look here to see what did you need to do to each of these to get to the same amount. So if I have 1 and 5, the logical answer would be 5, right? If I had 2 and 5, the answer would have been 10. And that's all. 2 and 3 would be 6. 1 and 2 would just be 2. You just alter the one that you need. So I have 5 moles of electrons. And again, that's only a point. So you just got to take a look. Letter D. Calculate the value of the equilibrium constant for the cell reaction. Explain what the magnitude of K tells you about the extent of the reaction. Okay, so again, there's an equation. Can you look on your orange sheet one more time, please? We had this like a week ago. I want you to make sure you can find this one. So you'd find the electrochem area. And if we're looking for K, now this is 2010, so potentially they had different equations on there. What do we got? So here's the thing. They have this. Hunter, can you say that to me?
Negative RT after log.
Can then you also tell me the one with the F in it?
Yeah, negative NFE.
So they used to have it's called the Nernst equation. This question will not be asked exactly like this anymore. Okay? The Nernst equation was all one thing. So honestly, it's a little confusing. So I'm going to give you the setup for this. Just understand this is a little bit in the past now. You can make these things equal each other and it turns into a new equation. So just write this down once. Just know, basically me saying this is the same idea as you, like, what I'm basically doing for you is here's an equation, could you have executed it? So even if you can't do it exactly the same way, what they probably do now is ask more in terms of this, or make these equal each other. So you can get this answer if you make these equal each other. I do want to talk about that. So you can punch this in right now. Would that be 0.72, right? That'd be 96,485, or whatever it says, right? What is N? 5. In electrochem, right, it's my electrons. Then if I make it equal that, that's going to be the 8.314, because that's with energy, right? That's the joule. And then we do our temp, which if you don't know the temp, or you couldn't find it, it's probably at 298. That's standard room temperature, which I'm sure it says it somewhere. But just if you're like unsure, everything's almost always done at 298. So that basically, these equaling each other is this. And you're like, well, what's that number? That's actually taking my Faraday's constant, my R, and my T. It's actually the final answer to that.
How does the ln become a normal log?
You can work with a natural log or log, and it affected this value. There's hidden math in this number. Just know that. So when it's all said and done, I guess I'm trying to kind of sidestep this right now, and I just wanted to talk about the important parts for you. We get this. So just kind of write this down because we're kind of skipping it. I'm not saying that you can't do it. I'm saying that in this context and what we've been given, they've transformed or evolved where they want. So this is the answer. Okay, I have full confidence that you've been able to answer that. They used to give you Nernst Equation. It's great. But you wouldn't have been able to do it if you didn't understand that and was 5. So you get a point basically for subbing all your numbers in correctly. So did you do the 5? You get a point for getting the K. And then you get a point for interpreting it. So when I get a number like that, what does that mean?
It's not all make product.
It is crazy spontaneous, right? Like not speed-wise, but like it's going to happen. It's going to make literally all product. There's nothing that's going to be left. So this cell is basically going to go to, what's a good word? Completion. This reaction is going to go basically to completion. That's what it's saying. There's no, when you have a K, that's equilibrium. Equilibrium means you always have a little bit of both. You always have some reactant, you always have products. This is basically saying you are going to be making product. So this is a very good cell. Like this is gonna go. Like there's no doubt in that. So that's what that means. I want to read it, their wording, just so you know, because the magnitude of K is very large, the extent of the cell reaction is also very large, and the reaction goes essentially to completion. Okay? All right. So that's great, but then we get to here. And this is where it gets difficult. And I had some work somewhere else that I tried to make it simpler. So I'm sorry if I stumble for a second because I wanted to make it a little more straightforward for you. But if we start reading it, it's okay if I can't find it. It's not like I don't know how to do it. The solutions containing Fe2 plus are one containing MnO4 minus and one containing H plus are mixed in a beaker and allowed to react. The initial concentrations of the species in the mixture are 0.6, 0.1, and 1. When the reaction mixture has come to equilibrium, which species has a higher concentration, Mn2 plus or MnO4 minus? Give me 1 sec. If I can find it, I like how I did it. It's okay. Okay, so here's the trick. Will Mn2 plus or MnO4 minus, that's the first one, be greater? So what you actually have to figure out is kind of what's going on here. So if you look at this equation right now, I'm just going to write this down. I have 5 Fe2 plus, 1 Mn, I'm not going to write the 1. So, you actually, realizing this or not, this is almost more of a limiting reactant problem. You have to figure out how much is going to go to the other side. So which one runs out first? So if I wrote these down on the bottom, and I had 0.6, and I had 0.1, and I had 1, do you look at those mole ratios a little bit? What one's going to run out first? Like if this completely goes to completion, what's left on this side is what I'm saying. So for every 5 of these, I need 1 of these and 8 of these, right? So who's going to run out first? Isn't MnO4 going to go? Because if I have 1 of these, I need 5 of these. Well, imagine for a second that this is a 1, right, instead of a 0.1. That's a 6, and this is a 10, basically. Right, so when it's done, doesn't it make sense that I'd have 0? How much would I have left here? If 0.1 was used here, don't I need to use 0.5 here? So wouldn't only 0.1 be left? So I'm going to use up. This is what I'm going to write on top. I'm not doing mole ratios here. I am, but I'm not physically showing you them. I use all that up. I use 0.5 up here, and how much of this am I going to use up? I'm going to use the 0.8, so 0.2 is left. Does that make sense? Like, you just think about it for a second. Well, how could you do that otherwise? You could do a teacher, right? You could say, hey, I have 0.1 times 5 divided by 1, and then it would say 0.5 needed. Oh, I have 0.6. I have more than I need. Right? Do the same thing. So what is that saying? That's saying that all this is going to be gone. And what's it going to do? It's going to create and go to the other side. So basically 0.1 moles are going to the other side. That's what it's saying. If it's a 1-to-1. And look, see how that's a 1-to-1? So if I consume all this, I make all that automatically. So the answer to this first one, and if you don't like the way I did it, I would have done t-charts then. Just compare it. I mean, literally compare it. But you had to know that this is going to be all used up. So the answer for A, or I, no, there's no I, sorry, E, which one's going to mean higher concentration? Mn2 plus or MnO4 minus? Mn2 plus, because the MnO4 minus has been consumed, and the Mn2 plus has been created. Or I have 0, based on limiting react, you could say based on limiting reactants, the MnO4 minus will be consumed, leaving only Mn2 plus present. Okay? So the answer is Mn2 plus will have a greater I will read what they have. They said Mn2 plus to be greater than Mn4 minus because, 1, as indicated in part D, the reaction essentially goes to completion. So you know it's going all the way to the right automatically. That's one way. You could have thought, well, wait a minute. If K is times 10 to the 60, I'm going to make product. That's actually a logical assessment. That would be right. I didn't do any math. 2, there is more sufficient F2 and H plus to react completely with the MnO4. MnO4 at equilibrium is essentially 0. 1 point is earned for the choice of Mn2 plus with the explanation, including only one item that I just said. Only 1 point is earned for including item 2. Wow, interesting. So I've only gotten 1 point by doing this work. I would have also had to say, sorry, I have to, is that me? Sorry, this is what my daughter. Nope, okay. I've only gotten 1 point. I should have said then, because it's an equilibrium problem, it will be consumed and create more MnO2 plus because of limiting reactants, and the fact knowing that the K is so large, we know that it will be driven completely to the products, or something to that effect. So I would have only gotten 1 of the 2. You know, I feel like nowadays, because this is 2010, I think they would have probably made D and E, and then F. They would have probably made this a letter D, I, double I, triple I. Because then they would have found that K, and then you're like, wait a minute, I just found that K. I's, double I's, and triple I's, you kind of, they're interwoven more, and I think that is a helpful thing. All right, F. I'm curious what you have to come up with on this. And I know I'm trying my best not to do the work, but I kind of feel like I am. I'm going to give you a moment to try to do this. When the mixture has come to equilibrium, what are the molar concentrations of F2 plus and Fe3 plus? So think about what I just did there, okay? And see how you can relate that. So I'm going to pause this for a second. It's a good question. Okay, what did we say? Anybody want to put themselves out there for a second? What do you think? How much is left? Or how much is it? Dylan, what do you got?
I have 0.1 for Fe2 plus and 0.5 for Fe3 plus.
0.5?
Yep.
Did I write it right?
Yeah.
Okay. So you're saying, based on my work up here, is that afterwards we had that, right? So we're saying that that much is going across. So what's the mole ratio of the Fe3 plus on the other side?
5.
It's also 5, right? So shouldn't it make sense that if this is a 5 and the other product is a 5, that whatever is being consumed will be created in the same amount? That's all. And that is exactly right. That is the right answer. So 1 point is earned for the correct setup. And you could have done any which way. So if you had done this, that would have helped. And 1 point is earned for the correct numerical value. I know some of you need to go. I am going to be doing the other problem, and we're going to do that right now. And then we'll go over some of our finals. How many people are leaving?
Everyone. Wait. Me, Hunter, Kayla, Connor, and
So not everyone.
I'm not.
It's not even.
5 out of 12.
So 5 12s.
Pretty close. 5 out of 12. That's pretty close.
Good. I mean, not good.
Somebody had a quick bag. Somebody had a quick bag.
Zach's like, walk on. See you guys. All right, here we go. Let's look at this last problem. What number is this? 2000 what? 6? D? Okay, here we go. This is a good one. So, does this complete our packet then?
Yeah.
Perfect. That was the goal. Even if you didn't like it with the OCD, we come full circle. A voltaic cell is set up using Al and Al3 plus as one half cell and Sn and Sn2 plus as the other half cell. The half cells contain equal volume. So first off, guys, understand, right, this is my metal, that's the solution, right? This is my metal, that's the solution. So it's like, and I might have to draw this, but I'm just going to draw, like I have, if you're really not sure what you're reading, is it something like this. Now, I don't know if it's this order. But that's what it's looking like. Right? What is that? That is my cell bridge or a porous disc or something like that, right? If it's not drawn, you need to draw it. It's not asking to draw this. I'm just, like, if you were given that stuff, that's the cell. Freaking me out. So here we go. A lot, oh my gosh. We have I, double I, triple I, IV. I love it. I, write the balanced net equation for the spontaneous cell reaction. Okay, full disclosure. How do you know which way it's going to go? What do you have to be given? You have to be given reduction potential reactions, okay? So you'd have to look, which one do I have to flip? And when you flip it, then you'd see where the electrons are. So unfortunately, we don't have that right now. And I could ask you to look it up and get your stuff out, but I'm going to give this to you, okay? So you would have to have been given more information, unfortunately. So based on my picture, and I'm going to just jump right into this because it doesn't ask for you to draw it. Based on the picture I drew, which way are the electrons flowing then? If I gave you that equation, if you were given the equation, you should be able to say where the electrons are actually going. So if I look at this right now, the way I drew it, and that was just totally arbitrary. I don't have a picture drawn. I did it on my own right now. Is what it's saying is aluminum is becoming an aluminum 3 plus, right? And what it's saying is that the ion of tin is becoming the solid of tin. So what it's doing is that this is going into solution, and this is plating onto the electrode. That's what it's saying. So how do I go in the solution? How do I go from an Al to an Al3 plus? Is that gaining or losing electrons? Is it gaining? If you gain electrons, don't you become more negative? And did this become more positive? So aren't 3 electrons leaving this so this could happen? But just stay with me on this. And maybe the answer is not 3 here. But then to become a solid, I have a 2 plus. The only way that it would become basically neutral again is if it added negatives. So the negatives are coming down onto here, and then it's combining and plating. Which one's getting bigger? The tin, because the tin's actually plating onto it. I think these are really important things to be drawn because we haven't had these lately. What's happening to this one? It's getting smaller, right? Like those are things that could be asked. Hey, which electrode's losing mass? Which one's gaining mass? So, I'm jumping ahead, but how many electrons am I actually dealing with here? Look at the equation once. Isn't it 6? 3 times 2? Isn't that 6? And 6? So this would be 6 electrons flowing, not 3. If you have a 2 plus and a 3 plus, you had to have lost 2 and 3 electrons. So 2 and 3 is 6. So that's how that one works. By the way, if you got this answer, which we couldn't in the context that we had it, it's 2 points. 1 point is for the correct direction, if you flip the right thing, and then 1 point is earned for having it as a net ionic that way. Double I. I've probably gotten ahead of myself. Oh, jeez. Determine the values. All right, we need some numbers. Let me ask you this. Which one did I flip? The aluminum or the tin? So the one that I flipped would have to have the electrons down on the other side. So that means they're losing the electrons. So aluminum. Initially, just to kind of hammer this home, if you want to quickly write this down for a moment, this is what it would look like. I think it's important to see it. And I'm going to tell you now, these are the oh shoot, I don't know which value is which. So I'm not going to try to guess that. So I would have looked at that. I would have taken the smallest number, right? I would have flipped it. Clearly, the smallest one is aluminum. So you know what? I will take a guess. I think it's this. I think that's what it is. So if you were given those things, that's what it is. So they're both negative. Isn't this from last problem? So which one do I flip? I flip that one. So my answer, if I add it all together, would be 1.52 volts, right? I flip that one, right? I got to flip it. Yep. 1 point. Potential's got to be positive, guys. That's the key to that. Triple I. Calculate the value of the standard free energy change for the spontaneous cell. Again, okay, so actually I think we have this one. So if you want to look at your orange sheet, it says calculate the G. Is there a G talking about one with a cell? NFE? Negative NFE? Yeah, so I hope I've trained you enough. Always write it down and then move on. Write it down. Establish what you're working with. If you just write numbers in and have not established what you're working with, they may not know what you're doing because you might not be doing it right. Okay? So that's a problem. So I'm going to go, so negative, and then my first number I'm going to write is 6, right? 6. And if you're writing, just stop for a second, look up. You would get that much easier. If you saw these two, I think you all would say, oh, that's 6, right? If you just saw this, that's a little harder. But you can notice that, oh, what's the overall charge? If it's an overall 8 positive, you're going to have 8 electrons. I don't think I've ever seen something like that, but that would be, well, a 2 and a 4, you just bring the 2 to a 4, so that would be a tricky one. F, you just multiply by Faraday's constant. And again, a lot of times we round it, but if the orange sheet says 46,485, then it's 46,485. I usually see it as 46,500. And then the E. What is that? Whatever you just found. So it's 1.52 volts. It does not give you an answer of what unit it is. So if we calculate this out, and you get it, it's something like, if you want to try it, you definitely can. I'm rounding, I think. Whoops. Didn't mean to write that. If you got that number, backtrack 10 seconds. You get that number, logically, that's probably in joules, right? That is a mammoth kilojoule. And that everything that we've ever done, you're not going to get some magical new technology of a cell where we're just getting all this extra energy. So that should be joules. So it's your call, and if you ever forget the moles, it's okay. It's okay. But it's your call if you want to change it. A lot of times they'll ask you for it in kilojoules per mole, but if they haven't, it's your call. When I get over 10,000, I usually go to kilojoules when I'm doing joules. But you've got to read what unit they want. You don't know the unit, or if they don't ask for a specific unit, then it's your choice. By the way, that is probably 2 points. Before I look at it, I bet it's 1 point for getting N right, and then 1 point for the proper answer. 1 point is earned is for indicating the correct moles of E, and 1 point is earned for the correct answer with correct units. So that is very common. They want to know if you're understanding the electrons. Last one. The cell operates until the aluminum concentration is 1.08 in the aluminum 3 plus half cell. What is the tin concentration in the SN2 plus half cell? Wow. Okay. So you can do this in a couple ways, but basically here, let's talk about this. This is why I like drawing these things. If you don't know, do you know what the amount is in a standard cell in the beginning? What's the molarity? You guys remember? It's a standard amount. If you had to guess, what is the concentration before you start? 1 molar. Yeah. I don't know if it says that. I'm just telling you. So in the beginning, it's 1 molar. Like that. I think that's something that's I guess, assumed you know. So I don't think everyone would know that. So now that it's increased, I think, bless you, I think, operates until 1.08. So this has gone up. Does that make sense that that's going up? Looking at my picture, the concentration of my ion. Aren't I plopping more ion in there, right? Isn't that makes sense? So when does this cell die? The cell doesn't die if that will never run out. The cell dies if I run out of aluminum metal, or what's the other thing? Well, besides salt bridge, I run out of aluminum metal or I run out of tin ion, right? Isn't that what's actually going to die? Because I'm never going to run out of tin. I'm only making more, right? So either aluminum metal or the tin ion, besides obvious issues like salt bridges and flipping of switches if the switch opens up, all that stuff. So this is going to go down. So this is how I would do this. And there's a couple ways. If you don't like it this way, you can definitely think of another way. If you can think about it as the change. I made 0.08 basically moles of aluminum per 1 liter. We're just going to keep the liter there. So all I'm going to do is compare it. If I look at my equation, now if you want to do 1.08, it probably will work. We could try it. Shoot, I wanted to be closer. Here, I'm going to bring this down. So when you're converting, when you're ever asked, hey, I made this much, or I have this much of something, how much do I have of something else? Think T-chart, please, even when it's not in that context. So what am I doing? Well, for every 2 moles of aluminum 3 plus, I have 3 moles of tin. But that's it. I mean, that's all. All I got to do. It's just going to say, well, if I made that much, then this much will be equal to that. Can someone calculate that exactly? I think it's a 12. It's 0.12. Sounds right. So what does that mean? If this much was made, then what is that? That's how much was taken out. That would be the reflection of it. So then you just got to take 1 minus that. So my final answer for my concentration would be 0.88, right? I'd have 1 molar minus 0.12 molar. Is that confusing? Yeah, I don't think that's horribly straightforward. Guess what, though? It's 1 point. So for being resilient and moving forward is the mantra always. You got to just keep pushing. So if you don't know it, do the best you can. But I guess I'm trying to have you recognize, like, you're not necessarily in an electrochem problem. You're just in a chemistry problem. It said you had an amount of one. You want an amount of another. Another way you could have done it, let me just bring my calculator up here. I'm not texting. Yeah, that wouldn't work. Yeah, that's the way you had it. Okay, I think there's just a letter B. In another voltaic cell with the aluminum and tin half cells, the concentration of Sn is 0.01 and the aluminum is 1. Calculate the value in volts of the cell potential. Oh. I see this might not be valid anymore. So let's talk about it in a different way. Would the cell potential be greater than, less than, or equal to the current cell? Okay, so the current cell, we have 1 and 1, right? Now what they're saying, let's talk about this in a different way. So we have 1 and 1 right now. And that 1 and 1 makes, what do we have, 1.52? Okay, what they're proposing is that if I have a point, so if you want to rewrite this, because this will be more of what they would ask now. There's a mathematical way to do this. Okay, you're using concentrations and all that stuff, but it's not on our orange sheets anymore, so it's not expected that you bring that up. But I could see them going, oh, now it's altered to this. Will the cell potential increase, decrease, remain the same? First off, cell potential is basically how long can you transfer those electrons. The longer this can run, the higher the voltage. That's what that is. So, can this last longer or shorter? Why? So it literally just fell into place of what we were talking about, right? Isn't this leaving? As this is going, this is naturally decreasing, right? And as this is going, this is naturally increasing. So if you would have flipped it with that, what would have that have done? Well, honestly, this would have done nothing. If you flip this, stay with me. I know we've had a long week. I can see it on their faces. But no change. Why? Because that is still the same value. They would have been the same. But in this case, though, it would be less. And if you want to know the numerical value is like 1.46. But it will be less. So that would be kind of maybe a way that we could talk about it. All right. Was that all that's on the problem? Is that it? Yeah. Super. So that concludes our big idea number 3. It's chemical reaction.